All right, well, welcome back. So today this is a colloquium talk designed for my introduction to machine learning class. And today's topic is on neurosymbolic AI. And just as kind of an overview, this talk is really about sort of the bare basics on neurosymbolic artificial intelligence. What is the main idea behind it? Why do we think we need it? And all we're assuming is kind of a basic knowledge of contemporary machine learning and deep learning techniques. Okay. So anyway, neurosymbolic AI. So, why is this of interest? Well, first, let's consider, currently what we have in AI. So this is the state of the art really is all about supervised deep learning, or supervised, or put slash self-supervised if you want to make sure we're including the latest generative AI stuff. And so let's talk about what these things do well. So first off, they are really good at mimicking the distribution of the test data set. Okay, and this is really quite obvious. The other good thing about it is that we can we're fairly mature tools are available for this today. The other thing is accuracy numbers for tasks such as vision are very high. And then I'll put a note here, though, when the test samples are in the distribution of the training data. And so, and I think also it is fair to say there is, a good amount of flexibility in the design of the neural network. So pretty much you can do whatever you want as long as it's feed forward. So that's, pretty decent list of some of the pros. So what about the cons? What are some things that are not good about deep learning? So, to start is, the number one thing is they're very dependent on the test data. And as a result of that, they don't perform well with previously unseen classes. And so one thing you can think of here is there's been a whole lot of engineering that has been around, hey, what can we model as a supervised or self-supervised machine learning problem? And at some point, you just can't do much more. So for example, if I have a bunch of different things in an image that interact with each other, and I want to be very accurate in terms of identifying image or items in an image that interact with each other, to have consistency in that, really the kind of, you'd have to have labels for every combination of objects. And that is a combinatorial explosion. And then on top of it, you'd have to have a whole lot of samples for each of those combinations. This is an example of where the whole paradigm of supervision starts to fall off a bit. And this is not to mention the fact that that data, just may not be available, and that's something that is often true. We as humans don't need extensive data sets to do simple reasoning tasks. When you learned arithmetic with, say, three-digit numbers in grade school, you didn't have to memorize all arithmetic operations with every combination of three-digit numbers that were added together. You learned an algorithm on how to do that addition operation, and that could generalize to things that were never seen before, and you didn't have to rely on rote memorization. And so this is a capability that deep learning just can't do by itself. The other thing that's an issue is lack of modularity. Now, deep learning, in terms of the design of the system, yes, you have a certain type of modularity where you can have a pre-trained layer and then you can fine-tune it with adding additional layers and things like that. But once that model is trained, you're done. You've lost any sort of modularity from that point. You just have this black box that performs really well on data that comes from a certain distribution. Whereas if you think of things like components in an automobile, you can get components such as a light or a steering wheel, and it could potentially work on many different automobiles. And that's why you see things like auto mechanics that specialize in American cars versus German cars versus Japanese. That's because a set of pieces that are common across those models are available to that mechanic, and they take advantage of this modularity. Once the model is trained, you've lost modularity. There's nothing you can do to really adjust the model without going back and doing retraining. And this has some, big implications for things such as aerospace and robotics. So along those lines is we do not have the ability to enforce constraints. So we can't design a neural network that we can be assured is not going to provide a certain output. We can train and fine tune, and if you're at OpenAI, do things like reinforcement learning with human feedback to try to identify cases that we don't like and have the model avoid that, and that could be done very well. So that is possible, but you can't have an assurance that it will never take a certain action. Whereas when you look at things that are very mission critical, such as just standard computer systems that keep the power grid going, such as software that runs in spacecraft that NASA sends to the other side of the solar system, or military systems where you need to make sure that, say, your unmanned aerial vehicle does not fly into airspace where a jet is operating. These kind of things you can't enforce with, a straight deep learning architecture and ensure that those guarantees are met 100% of the time. And those applications that I mentioned, you really want to be able to enforce these very strict constraints. And so things like reinforcement learning with human feedback, they just won't cut it because they're not going to block off, all paths to a given bad outcome. And that's why you see a lot of deep learning systems today, they tend to be applied to consumer problems where the cost of getting things wrong is actually pretty low. And so kind of tied in with all of these is, the lack of ability to reason. And the big thing with neural networks is they're really designed for perception. So if you look at this from an AI perspective, neural networks are designed to take information from the environment and make a very rapid decision about what is in the environment. It's not about thinking about planning or what it's going to do. There are some pieces of work, and especially lately with large language models that start to, that try to push these paradigms toward being able to reason. But time and again, it shows that these things start to fail when it gets confronted with a more challenging problem. One thing that has been seen in studies over and over again, when a neural network model encounters a problem that requires multi-step inference, even if they do all kinds of special stuff to make it be able to reason, as the number of inference steps increases, the performance decreases. And that is really odd, because in no other piece of software do you really have, do you just start getting errors just because it takes longer to reason about something. The correctness of it doesn't really change, where you have this steep drop off in performance when you start getting into multi-step inference. So that's kind of the state of deep learning. Many of, and this is not to say that it's not useful, it's highly I'm a big proponent of it. I think it's, it's very important, and it's accomplished a lot. But there are, like any technology, there are certain limits. So with neurosymbolic, so that's kind of, the neural side. Well, what about the symbolic? What does symbolic do well and, bad? So let's go with, symbolic AI. So just really quick, for those of you who don't know what symbolic AI is, it's basically using ideas such as logic or formal mathematics to reason about something. So we say, if A is true, and the statement, if A then B is true, then we can conclude from that that B is also true. So we do the very step-by-step logical processes. And this is the whole idea of logic underlies just about everything in computer science. You wouldn't be able to write code if we didn't have logical underpinnings in computer science. Symbolic AI is all about taking these ideas and using it for AI. And so you may have heard of things such as expert systems, Bayesian networks, cognitive models. Those are all examples of symbolic AI. So what have these things done well? So let's do the pros. So the first thing is they can provide reasoning. They, so the whole, all logical systems were designed for this. So this is one place that they particularly shine. The other thing that's nice about logic is it's modular. So once you have a logical theory, if you want to add additional stuff to that theory, it's much easier to combine logical theories than because it's inherently modular. So if I were to say, hey, give me, if you think of a math problem, give me an x and y that satisfies x plus y equals 9, and you give me two numbers, and I say, okay, now give me two numbers that satisfies that constraint and the additional constraint of x minus y equals 2. And so you can now solve that problem as well with the same type of reasoning. And this idea of modularity, is very powerful, and it allows you to build things. Another thing is, does not need training data specific for each combinatorial outcome. So we can have things that, are not necessarily in the training data. So like I said, in the example of looking at adding 2 3-digit numbers together, if we have a system that's designed to do that addition, we don't need to have training data for every combination, a 3-digit number out there. And so then the final thing is, I would say, that's really important here is ability to enforce constraints. And this is 100% of the time we can make sure those constraints are enforced with the symbolic AI system. All right, well, that sounds really good. Well, how come we use neural networks and not symbolic AI systems for reasoning? Well, the cons are, difficulties. Because they're inherently not data driven. And so the really great quality of neural networks is that you can take a bunch of data and you can train a neural network for a task if you know that the environment that network is operating in will look like that data. And it can arbitrarily get better with the more data you have. And this is why things like ChatGPT work, because people are using it on the internet in natural language, and it's sort of mimicking responses to that natural language based on old natural language from the internet. And so something like an LLM is really good at that. It's very difficult to train a symbolic AI system from data to be able to get the same results. So this is probably, the number one thing that is challenging about it. I would say, the other thing is that that would be challenging here is, I would say there is not the wide amount of tools available. And I think this is a little bit of a chicken and an egg thing, because one of the big reasons why we have such good tools for neural networks is that large companies saw it was advantageous for them to create or contribute to open source projects in order to develop a community around tools that are useful for their business. So, Google released TensorFlow because when they started to realize that neural networks were very powerful, they needed to hire people that knew how to do this. And if they figured that if they released software that would allow folks to experiment with it and get good, they sort of create that workforce. Facebook, or now Meta, did the same thing with PyTorch, except instead of releasing their own, they became significant contributors to an existing open source platform that was available. And so both those companies were doing this to build the workforce. And as a result, those tools got really great. Because we haven't demonstrated, consumer grade use cases for logic that are relevant to these big money making companies like Meta and Google, we don't have as, as wide or as mature tools available as we do on the deep learning side. And so that is a big problem. Okay, so here we have the pros and cons. And so Neurosymbolic AI is all about, combining these things together. So Neurosymbolic AI, we want to take the ability to mimic the world from deep learning and enhance it with the reasoning capability of symbolic AI. And that's kind of the big thing. And if you want to think about stuff that we can get out of that, first, so here are some, here is the vision of Neurosymbolic AI. NSAI for short. So first is you can train the model and simultaneously embed constraints and or domain knowledge. So here we think about a neural system where we say that, hey, we want to optimize our loss function as normal based on a set of labels, but we enforce a constraint. So, for example, we're looking to recognize a scene, and we're looking at the different objects in the scene. And if we see, if we see someone wearing a baseball hat with a baseball bat, and he's on, and he's in a baseball diamond, that we will also conclude that other people in that area will also be baseball players, not playing some kind of other sport. If we think about things in the action domain, we can think about enforcing constraints for things like ensuring safety, ensuring airspace deconfliction is abided by. And if we can enforce these constraints on the model during training, the resulting model can adhere to those constraints. And we can look at either soft constraints where we don't have a strong assurance that the constraints will be met, but we know most of the time that will be true. Or we can look at hard constraints as where all the time the constraints need to be met. So the idea is, in a combined system, you can have that capability. You can do both perceive things and also enforce domain knowledge. So that I'd say is sort of one really big thing. So two is we can take perceptual information and then manipulate it with some kind of logic. And now, so this is looking at a little bit different. So here we have the perceptual model, which is neural. And in many cases, this will be something like a vision model. And we train that on some data, and we use it in a component, say a camera system on an autonomous vehicle. And then whatever is recognized in the images from that camera system is used in a more logical process to make decisions as to what action the vehicle will take. And so you could think of this as, if you watched my System 1, System 2 video, you have a System 1, which is perception, so instantly recognizing things, and that's a neural network. And this is like, for example, if, you look at the letter A on the screen here, well, you instantly recognize it's an A. You can't really describe what makes something an A, and you learn that because you saw, the letter A hundreds of times as a child. Whereas when you start to assemble the letters, maybe you never saw the word neurosymbolic before, but you can read those letters and you can assemble it in your mind, and you can read those words, and now you can put together what's on the screen here. And so that is a System 2 operation. You're doing something that is more logic oriented, but based on perception. And this is kind of a big thing. How do we take perceptual information and act on it, especially in stuff like robotics and autonomous driving? This is really important. So the next aspect is we use logic to correct the output of a neural model. So this is a little bit different, but here's an example. So let's say, so let's say that you drop a friend off at the airport, and that friend is leaving to another country. Let's say they're going to like Europe or something far away, and you're here in Arizona. And then on the way back from the airport, you go to like a coffee shop or something, And at first, from a distance, you see someone that kind of looks like your friend. And instantly, you start to recognize that individual, and you're just looking from a distance. But you know, after thinking about it for, about a minute, you're like, no, that can't be my friend. My friend is on an airplane. I just dropped him or her off at the airport. That second step, where after you recognize someone as being your friend, and then you thought about it and you thought, it can't be, I dropped that person off at the airport. You're now adding some external context to it. You still instantly perceive that person as being the friend that you dropped off, but putting it into context based on this additional knowledge that you have, you corrected that error. And so deep learning models are really good at that first part. But sometimes this is why you get weird results from deep learning, because it's simply matching the patterns in what is perceived with something that resembles the historical data. And this is why sometimes you've seen examples where there are weird things, like a car with a certain pattern on its hood is recognized as a birthday cake. Now, clearly that makes no sense, because especially as humans, we understand the context of an image. Even if it's a really unusual looking car, we still see the wheels, we see the road, we put it into context, and we know right away it is not possibly a birthday cake. So this is kind of the third big use of it. There is one more use, and this is a little bit different, and this is the use of neural optimization methods to learn symbolic knowledge bases. Now, if you've been taking the lessons in the course, this CSE 475 Intro to Machine Learning, in the last unit, there is a lesson on rule mining and the a priori algorithm, which admittedly, this is something more data mining than machine learning, but I think it's, we included it because we think that this is a really important thing to be aware of. Now, rule learning is nice for identifying patterns, but it has its shortcomings in that sometimes it's kind of overfitting to data, it's not considering the data globally, and so on. And there are approaches for learning symbolic knowledge bases, such as a set of rules, using gradient descent and neural architectures to overcome some of these issues. And this kind of gets to, this thing right here, where difficulties in training a symbolic system from data. And so a lot of that work is kind of in its early stages. But anyway, those are probably sort of the four big things to understand. I mean, potentially we can add a fifth, that is, there are neurosymbolic approaches to this, and there's non-neurosymbolic approaches to this. This would be analysis of why a neural network produces a given result. So one big complaint of neural networks, and I should have listed it here, is they are black box systems. They are opaque. They can't explain why they got a certain result. And there are people who are doing research on analyzing which neurons fire in the neural network to give them insight into why a given result was produced. So let's get rid of some of this stuff and bring up kind of this idea, this vision of neurosymbolic AI, and talk about, I didn't want to narrow there. Talk about some of these individual things. So first is training a model from historical data and embedding constraints in our domain knowledge. So there are a couple of approaches to this, and the software is available today. And so let me see if I can highlight this. Okay, so this first one, and then we'll unbold the rest. All right, so what are approaches for this? Well, so basically what we want to do here is add constraints to the learning process. So there are a couple frameworks out there. So one is called logic tensor networks. Another is called logical neural networks. Another is called deep problog. There's another one called semantic loss. And there is SPL, and then there's a bunch more. Okay. So, but here's sort of the basic idea is you have a neural network. So let's just represent this as a box. And then we'll say that that we have an input perception, and then we have output class labels. We have an input perception and we have output class labels. There we go. Very simple. Okay. And in that box I have on the screen, you have all your neural layers, and at the top you have you have the outer layer. So what happens here is we want to have these weights be learned in a way to adhere to some kind of logical rules. So we don't want the helicopter to fly in the airspace where the airplane is. We don't want, we don't want the train to, go over a certain speed. We don't want the autonomous vehicle to to take hairpin turns when there's significant rain outside, and so forth. So we have all these constraints that we know we want to avoid, or we want to use some domain knowledge to imbue into the system to help the training process. So what we have here, is instead of we have some kind of mechanism, and I'm purposely, being a little vague, and we have this as a domain knowledge. As some sort of logical statements. I'm using logic, very, very loosely here. And so there's kind of two major ways we can represent the domain knowledge. So the way I have it written here is domain knowledge encoded as layers in the neural network. So what we have here is we have what was maybe originally the outermost layers becomes input into additional layers that are representing logic. Now, we may have some parameters on that logic. In frameworks like logical neural networks, we adjust the meaning of the logic slightly. In others, we don't do that, and the logic is pure. But the point is that this domain knowledge is directly encoded. An alternative way of doing this, and let me just copy that over. And let's see, does this allow, we can zoom out a little bit. Here, the domain knowledge is integrated into the loss function during training. And so here we'll have something like So just to kind of draw it out a bit, something like that, right? Where you do the training. So, and what happens here is there would be multiple terms in the loss function. So you would have one of the terms would be about how the loss function or how the neural network is fitting to the data. And this would be mean squared error or cross entropy loss, just like normal neural network stuff. But there would be an additional additive term that would deal with how well that the output of the neural network adheres to the constraints. And that in that part of the loss function is going to leverage these logical statements that, in something like logic tensor networks, you kind of input those into the system and it compiles a loss function for you. Now it starts to make sure that that the loss is taking into account these constraints. And this is also why often loss function based approaches like this are going to tend to be more along the lines of having a softer constraint. Okay, so enough of that discussion. So let's move on to the next piece. Oops. Let's unbold that and then let's do the next one. So take perceptual information and manipulate it with logic. And so what we have here we're starting to get into this idea that that such systems, well, hold on here. There we go. We get into the idea that such systems that are trained are being used as a perceptual module for a downstream reasoning task. And again, the big one here is autonomous driving. So what you will have is you will have your neural model, and this might be for the camera. And then you have like a second neural model, maybe. For say the LiDAR, which is common in AVs. And then you have, let's say, a planning module, and that is symbolic. So the planning module is now considering what the above two items are telling it in this approach. Now, in some cases, the lines can start to blur between this approach and the first one if what we're doing is we're taking that planning module and we're somehow using it to propagate a gradient through it. So there's approaches that actually, if you have this, but particularly with one neural model, you can then propagate a gradient, like this. Okay. But this ends up being quite expensive in practice. So usually that's not done. And instead, the approach is more of an engineering approach where you have, multiple neural models for various perception items, and that the logic or planning module that is used to combine them they're kind of designed in a way where things are iterative, and they're those models that are perceptual are trained by themselves, and then they're integrated with the planning module, and the whole thing is tested out end to end to see what kind of results it gets. All right, so the next thing is looking to use logic to correct the output of a neural model. And so here what you have is you have neural model, and that gives you some kind of output. and then you have some kind of logic model, with domain knowledge. And so that output is going into that. And then coming from that, you have corrected output. Now, in some research, this is actually looked at in kind of an end-to-end thing where you as you're training the neural model, you train the neural model, complete the training, and then you are testing it and seeing where the errors are in the domain knowledge. And based on that, you are now correcting those errors using the logic model, and you're using that information on the corrected errors to somehow generate a new sample that is then used to retrain the model. So in some cases, you have this kind of outer loop, sort of say, on the training regime. But there's also work where it's just simply looking to do this directly on the output of the neural model without involving anything with the training regime. And the advantage of why you'd want to do that is have some kind of error correction for your neural model to detect if maybe this error correction will help identify if it's in an environment where it's operating outside the training distribution. Maybe the neural model is something behind a company's API and you can't really change it. These kind of things is why modifying the results using some kind of logic that puts that context into play is useful. So then the next one is using it to, so the last two are more research based, and let's talk about them together here to wrap up. So in using neural optimization methods to learn a knowledge base, here you have a neural network that is neural network corresponds directly to logical symbols, and the network itself can directly translate into logical sentences. And basically what's going on here is the gradient descent process is being used as a way to explore different possible logical rules that can be learned. Now, the key thing of why this is challenging is logic is inherently discrete, where neural networks are operating with continuous math. And this kind of discrete versus continuous thing is that's kind of the biggest juncture between neural and symbolic methods and what makes them different. People who disagree with the idea of neurosymbolic AI often point to that as, hey, this chasm is too wide to traverse through. However, through things like fuzzy logic and real valued logic, where you can sort of mix scalar values with discrete values, you can overcome some of this. And so a lot of the work on learning a logical knowledge base hinges on this. And then as far as how these things go in terms of methods, kind of the common things we see are gradient, so there's gradient descent trained decision trees. This is different from gradient boosted decision trees. Here, we're actually using gradient descent to train the trees, unlike with gradient boosted trees. And this is taking essentially a top-down approach to producing that symbolic structure. A decision tree is a symbolic structure. Another thing is, very experimental right now, differentiable inductive logic programming. is another one. This takes a very top-down method. These things often suffer from computational complexity issues, although the gradient descent trained decision trees are actually showing some promise. But again, a decision tree is a very limited structure. And so to wrap up this discussion a bit, let's talk about analysis of why a neural network produces a given result. And so here you need to think of examining cases of when a neuron fires versus when it does not, based on information about the sample. So maybe you have a multi-class classification problem, and you're reasoning about if a boat is in the picture. You may also have samples that have something like fish, as well as maybe people hiking, and you can look at all those pictures that have a body of water in it, and you can start to identify neurons that actually are firing when that body of water is present. And so this is a way to understand what's going on within a given neural network. Now, the approaches here are not limited to neurosymbolic ones. It's just that because of the fact that we're trying to identify when something is occurring versus when it's not, this starts to have this discrete feel to it, and you get more, and it starts to border on logic, which is where neurosymbolic kind of things can start to fit into. So some common approaches here would be things like neural network introspection and counterfactual reasoning. So, neurosymbolic AI, it's, still a growing and emerging subdiscipline. While most of the work, like what's on the screen right now, involves research, some of the things, especially, in these first two categories, where you have things like logical tensor networks and SPL that are available today, as well as taking perceptual information and manipulating with logic. There's been a lot of success in doing that. And even some of the things using logic to correct the output of a neural model. There's things like ABL and now EDCR from ASU's research that can start to do this. So we are seeing some evidence of the promise here, but at the same time, please keep in mind that many of these things are still in the research stage. One thing to consider if you think combining a neural method with a symbolic method makes sense to you is, does my problem benefit from the addition of domain knowledge? And will the addition of domain knowledge maybe help my model do a little bit better in environments that start to differ from the training data? Those would be kind of the two big things to think about if neurosymbolic is appropriate for your problem. And I think the practical thing about it is that domain knowledge readily available? Now, there are some cases where the domain knowledge may just be common sense knowledge, and there's all kinds of things like common sense knowledge graphs available in autonomous driving. There's knowledge about traffic rules and so on. So if that's available, neurosymbolic methods may be a way to use it. So anyway, I hope you enjoyed this kind of little diversion into neurosymbolic AI that some people think is going to represent, some future directions for this growing field. And I hope you enjoy the rest of your day. Thanks much.